What I'd like to do in this video is introduce you guys to a very interesting number system, which is a variation of the complex numbers, and it's called the split complex numbers. And I'd like to start this video by presenting you guys with an illustration or visualization. What I have here is I've randomly generated a bunch of random split complex numbers. Each one of these dots is going to represent a different split complex number. And I'd like you to have a look at what the effect of multiplication by a split complex number is going to do to each one of these points. So pick any one of these points and see what it does upon multiplication. There's one multiplication, and again, and again, and a last time. And hopefully what you're seeing here are these trajectories which are going to turn out to be hyperbolas. We have these hyperbolic shaped trajectories, and we also have these linear trajectories here. We have this trajectory here, which is going to turn out to be the line y equals x, and we have this other trajectory here, which is going to turn out to be the line y equals minus x. And what I hope to do is explain to you why it is that algebraically we're seeing these hyperbolic trajectories. Let me briefly review complex numbers, so that split complex numbers are a bit more intuitive. Now, in the complex numbers, the defining aspect of this number system is that we have this element called I, and I has the property such that when it's squared, it's equal to minus 1. And hopefully you saw in the last video, if you haven't seen that, I encourage you to check that one out too. In the last video I showed that if we have this I squared equals minus 1, then if we take two complex numbers, let's say a plus bi times c plus di, this I squared equals minus 1 generates the complex number multiplication. That is, when we multiply out two complex numbers, a plus bi and c plus di, we arrive at the following formula: ac minus bd plus ad plus bc I. And this is the new complex number that results when multiplying two complex numbers. And that's all made possible by this I squared equals minus 1 property. Now, oftentimes in math, you can discover something new by recognizing when something was arbitrary. Now, what was arbitrary about this I squared being equal to minus 1 was the fact that we set up this new object called I, and we set it equal to minus 1 specifically. Now, the idea behind split complex numbers is to recognize that this minus 1 thing right here was arbitrary. And what we're going to do here is we're going to create this new mathematical object, which we're going to call j. And it's going to have the property such that when j is squared, that instead of being equal to minus 1, as it was in the complex numbers, j squared is going to be equal to positive 1. And just like in the complex numbers, this j squared equals 1 is going to generate a multiplication. And let me show you what I mean by that. So just like in the complex numbers, a split complex number is going to be of the form a plus bj, where a and b are two real numbers, and we're going to couple them together to generate a new mathematical object. So I have one split complex number, a plus bj, and I have a second one, c plus dj, and what I'm going to do is multiply them together. And let's see what multiplication is generated by j squared equals 1. So I'm just going to distribute that a to both terms. So I get ac plus adj, and then distribute the bj to both terms. And by the way, I didn't make up the j. So I distribute the bj to both terms. So I get bcj plus bd j squared. And now we recognize here that j squared is going to be equal to 1. So we just have bd in this term here. So now I'm going to change up the order a little bit. I'm going to write ac first, and then I'm going to have plus bd. And these are going to be the real parts. Just like ac minus bd was the real part here, ac plus bd is going to be the real part here. And then we have two terms that contribute to the imaginary part. So the imaginary part is going to be AD plus BC all times J. So this is going to be our definition of complex number multiplication, or split complex number multiplication. That is, if I have two split complex numbers, I'm going to write them in ordered pair notation. Let's say AB times CD. Then the new ordered pair that results is going to be AC plus BD in the first entry, the real component. Then the imaginary part is going to be AD plus BC. So you can see here that all we're really doing is swapping out a plus sign for a minus sign, which was present in the complex numbers. But this plus sign is quite interesting, and it's going to make all the difference. And by way of more review, if I had a two-dimensional plane, letting this horizontal axis be the real axis, and the vertical be the imaginary axis, the complex numbers, a plus bi, if the complex number is in the form a plus bi, it can be plotted in the following way, where I go a units on the real axis and b units up on the imaginary axis. And we saw last time we had this natural concept of distance, which is the distance drawn from the point of interest to the origin. And we called this the modulus, or the magnitude of a plus bi. And we said that the magnitude of a plus bi is going to be the square root of a squared plus b squared. And this is motivated by the Pythagorean theorem. After all, that's the length of this line drawn from the point to the origin. Now, we can do a similar sort of thing in the split complex numbers. If we had a split complex number, a plus bj, this is the real axis, this is the imaginary. The vertical axis represents how many copies of j I have in that complex number. And a number may very similarly be plotted in that way at the coordinate AB. Now, for the split complex numbers, we're going to abstract our notion of distance a little bit. That is, we're not going to define the magnitude of a plus bj in the same way as we did in the complex numbers. Now, it is still true that if you take a line drawn from that point to the origin, the length of that line is still the square root of a squared plus b squared. But in the split complex numbers, we're going to talk about a slightly different definition of magnitude. And the way I'm going to define magnitude for the split complex numbers is going to be the square root of not a squared plus b squared, but a squared minus b squared. And hopefully you can see from that if I square both sides, I have the squared magnitude of a plus bj is equal to a squared minus b squared. Now, you may be wondering why I changed up the definition of magnitude for the split complex numbers. And to show you why that is, let me go back to the magnitude of a plus bi. Let me go back to the squared magnitude, just to make things cleaner, which was a squared plus b squared. And we discovered in the last video that if I take a plus bi times c plus di, I multiply two complex numbers together, take the squared magnitude, that this is equal to the squared magnitude of a plus bi times the squared magnitude of c plus di. Now, on the left-hand side, when you do all this multiplication out, what this left-hand side is saying is that AC minus BD squared plus AD plus BC all squared is equal to a squared plus b squared times c squared plus d squared. And this identity here has a long history. I think it's called the Fibonacci identity. I think it's actually called the Brahmagupta Fibonacci identity. And this is what makes this property possible. This property that if I have two complex numbers, x and y, multiply them, then take the squared magnitude, then this is equal to the product of squared magnitudes of x and y. Or equivalently, the magnitude of xy is equal to the magnitude of x times the magnitude of y. When we understand magnitude in this sense, motivated by the Pythagorean theorem. Now for the split complex numbers, if you define magnitude in this way, you don't get this property back out. That is, if I change up that plus sign up there to a minus sign, that identity is false. The left-hand side is not equal to the right-hand side. And what I'm going to prove to you in the next slide is that by changing up your idea of magnitude, that we get a similar identity that makes this statement possible. Let me now do that. So we had a plus bj, and we're going to suppose that its squared magnitude is equal to a squared minus b squared. I'm talking about split complex numbers now. So now what I'm going to do is I have one split complex number, a plus bj. I'm going to multiply it by c plus dj. I'm going to take the squared magnitude of that. And what I claim is that this is equal to the squared magnitude of a plus bj times the squared magnitude of c plus dj. And put more concisely, if I have two split complex numbers, let's say x and y, then the squared magnitude of that is equal to the product of square magnitudes of x and of y. So let me prove this to you now. So I saw that split complex number multiplication, after I do all the work, it's going to be written like this. So I'm just going to multiply these two numbers. I have AC plus BD in that first real part. And then I'm going to have AD plus BC times J. So the squared magnitude of that. I'm going to work with the left-hand side for now. And now I'm going to use this definition of magnitude. So this first part, AC plus BD, is going to be squared. That's going to be subtracted from AD plus BC squared. Just using that definition of magnitude. Now I'm going to square out that term there. So I see that's equal to a squared, c squared. I'm going to have 2 ac times bd. I'm going to write that in the order a, b, c, d. Then my last term is going to be b squared, d squared. And hopefully this looks familiar to what we did in the complex numbers. Then I'm going to have minus. I'm going to square out this term here. I'm going to have AD squared, which is going to be a squared d squared. Then I'm going to have plus 2 ABCD. I have ADBC, but I'll write in the order ABCD. Then finally I have plus b squared c squared. Now I'm just going to distribute that minus sign to all terms. So I have a squared c squared plus 2 ABCD plus b squared d squared. Then I have minus a squared d squared minus 2abcd. Then I have minus b squared c squared. And like in the complex numbers, I have that nice cancellation there. And now what am I left with? Now first I'm going to write a squared c squared, that first term there. And then I'm going to write this term here, which is minus b squared c squared. Then I'm going to write plus b squared d squared. Then finally I have minus a squared d squared. And now out of that first term, these first two terms, I'm going to factor out a c squared. So I have c squared times a squared minus b squared. And now out of the second two terms, I'm going to factor out a minus d squared. So I'm going to have minus d squared. So now this term is going to become positive. So I get plus a squared as opposed to minus. And then this term is going to flip signs as well. So I'm going to get minus b squared. And now you notice that both terms here have a factor of a squared minus b squared. So I'm going to factor that right out. So I have a squared minus b squared times what's left, which is c squared minus d squared. So you see here that this first factor here is equal to the squared magnitude of a plus bj, and the second term is equal to the squared magnitude of c plus dj. And that ends the proof right there. And you can see here, in place of that Fibonacci identity, I derive a very similar identity, which shows the equality between this line and this line right here. Now I'd like to reemphasize why this whole talk of this property that if I have two numbers and I multiply them to create AB, then take the magnitude, that this is equal to the product of magnitudes, why this is important. Now for the complex numbers, which I'll denote by C, we saw in the last video that if I select some b such that the magnitude of b is equal to 1, then that implies that the magnitude of AB is equal to the magnitude of A. That is, when I take A and I multiply it by this other number B, then the magnitude is unchanged. And graphically what that meant is that if I have the unit circle, let's say that's a unit circle, and I select some B, which is on the unit circle, and then if I had some arbitrary point, let's say A out here, now the magnitude of A is going to be the length of that line drawn to the origin, and the set of all points that has magnitude of A is going to be a circle swept out right there. And what we saw was that multiplication by B, if B is on that unit circle, multiplication by B means that AB is going to be found somewhere on the blue circle. That is, A gets rotated over to AB and it's being kept on the same circle. So that was the main point of the last video I made. Now, for the split complex numbers, we have this property as well, that the magnitude of AB is equal to the magnitude of A times the magnitude of B. But our notion of magnitude was a little bit different. Now, the set of all points that had magnitude of 1 in the complex numbers is the unit circle. Now, going back to the definition of magnitude, if I have A plus Bj, that's equal to A squared minus B squared. If I want this, then this is magnitude. Now, if I want this to be equal to 1, what is this equation describing? That should be a square root as well. What is this equation describing? The square root of A squared minus B squared. Well, if I square both sides, I get A squared minus B squared equals 1. In the complex numbers, the equivalent equation would be A squared plus B squared equals 1, which is the equation for a circle with radius 1, the unit circle. But what is this equation? Well, it turns out this is going to be a hyperbola, namely the unit hyperbola. And what this hyperbola is going to look like is it's going to contain the point 1, 0. And it contains the point 1, 0 because 1 squared minus 0 squared is indeed equal to 1. And it also contains the point minus 1, 0 because minus 1 squared minus 0 is still equal to 1. And the hyperbola is going to look like this. And it's going to be extending off in those two directions there. And we have the symmetrical one over on this side. And of course, all these hyperbolas are going to have an oblique asymptote, which looks something like that. That is to say, on these two branches of the hyperbola, all of these points have the property that their x-coordinate squared minus their y-coordinate squared is equal to 1. That is, I could pick at random some point right there. Let's call that one B. And that would mean if this point B is on this hyperbola, that the magnitude of B is equal to 1. So under this notion of distance, B is of unit length, even though it may not necessarily be on the unit circle. So we can think of magnitude and split complex numbers as identifying which hyperbola the point is on, whereas in the complex numbers, we can think of that magnitude as identifying which of the circles that point is on. And just like in the complex numbers, if I select that B such that the magnitude of B is 1, that is, I pick some B, which is going to be on the unit hyperbola. Any one of these points on the unit hyperbola can serve as a candidate for B. I have this property up here, that the magnitude of AB is going to be equal to the magnitude of A times the magnitude of B, but I selected the magnitude of B to be 1, so that means that the magnitude of AB is going to be equal to the magnitude of A. And what does that mean? This has an exactly analogous interpretation as before. Let's say I pick A to be that point right there. And remember, I suggested interpreting this magnitude as identifying which of the hyperbolas this point A is on. Now A is on, let's suppose it's on this hyperbola. Whatever hyperbola that's going to be on. Now what this means is that when I take the number B and I multiply it by A, the number generated, AB, is going to also be found on this blue hyperbola. So it could be found, for instance, right there, as long as it stays on that hyperbola. Just like in the complex numbers, multiplication by a unit number with respect to that magnitude doesn't change which circle A was on. That means that AB is on the same circle. In the split complex numbers, AB is going to be found on the same hyperbola as A. Let me make a few last comments about this interpretation of the split complex number magnitude as identifying which hyperbola a point is located on. I said before that this hyperbola, which is going to have the equation x squared minus y squared is equal to 1, is going to serve as the unit hyperbola. Analogously to what happened in the complex numbers, where we had x squared plus y squared equals 1, serving as the unit circle. That means that all points on this branch of the hyperbola or this branch of the hyperbola are going to have a magnitude of 1. Now, a few other things of interest here. If I take a look at this oblique asymptote here, this is going to have the equation y is equal to x. And now, if I consider any one of those points, which has the property that y is equal to x, and I calculate the quantity x squared minus y squared, I know that y is equal to x, so I can make the substitution. I can get x squared minus x squared. I just made that substitution there. And this is, of course, equal to 0. Now, what that implies is that any point located on this line, y equals x, is going to have a magnitude of 0. And using a similar argument, you can show that any point along this line, which is going to be y is equal to minus x, so I'll label that there, y is equal to minus x, will also have a magnitude of 0. And this is pretty interesting because in the complex numbers, there was only one point which had a magnitude of 0. There's only one complex number which has a magnitude of 0, and that would be the origin. Now in the split complex numbers, you have infinitely many points which have a magnitude of 0. So that's a nice contrast there. Now, speaking of magnitudes other than 1, let's say I had the hyperbola passing through the point 2, 0. Let's say that's 2. And I draw that in there. And it would have a symmetrical branch here. It looks something like that. And if you do the calculation, all the points on this hyperbola or on this hyperbola here are going to have a magnitude of 2. And furthermore, if I start considering the points up here in this this cone up here or down here in this cone, let's say I have plus 1 right there, and I draw the hyperbola passing through there, and I draw on the symmetrical branch down here at minus 1. Now any point on those two hyperbolas is going to have a magnitude of minus 1 if you do that calculation. And as one last example, I can go in the upward direction as well. Let's say I have hyperbola passing through 2 up there, and I draw the other branch down here. Any point on those two last hyperbolas is going to have a magnitude of minus 2. So you can see here that if I draw out the coordinate grid one last time, the zeros are going to be found on this x right here. These are going to be the zeros. Anything in this cone to the right is going to have a positive magnitude. And similarly, everything in this left cone is going to have a positive magnitude. Everything up here in this upper cone and in this lower cone is going to have a magnitude which is negative, and the zeros are going to be found on that x. One additional thing to notice too is that there's a very special split complex number which acts like 1, and it's going to be the complex number, split complex number 1, 0, which is located right there. So that's going to be the number 1 plus 0j. And this is special because if I take 1 plus 0j, or just 1, 0, put it another way, and I multiply by any other split complex number, a plus bj, what you're going to get out if you follow the rules is just a plus bj. And you can multiply on the left or you can multiply on the right, you'll get the same thing. A plus bj times 1 plus 0j is also equal to a plus bj. So this is the special split complex number that acts like the number 1, just like we had in the complex numbers. Now, I point this out because if I take another point, let's say I pick some point A to be out here on that hyperbola of magnitude 2, when I take A and multiply by this special number, let me call that B, AB is going to be found right there. So put another way, multiplying by the number 1 doesn't change the position of A when it gets sent to AB. And just like we were finding for the complex numbers, if I take some number which is located very close to 1, 0, still on the unit hyperbola, but very close, this multiplication by this b does almost nothing to a. But what it's going to do is it's going to keep a on the same hyperbola. So that means AB might be located right there, for example. And this is what's going to result in these hyperbolic trajectories. By multiplying by a split complex number, which is still a unit in length, it's going to keep the points on the same hyperbola, but it's very close to 1, so it's going to have a little bit of motion. It's going to cause a little bit of motion. And that's what's going to generate the hyperbolic trajectories. At this point, let's get back to that visualization that I first showed you. Now, what you're going to see me do in this visualization is I'm going to take each one of those points, each one of those dots, and I'm going to multiply it by a split complex number, which I call b, and this b is going to have a magnitude of 1. Magnitude in the split complex number sense, in the hyperbolic sense. And the precise number that I chose to multiply each one of these points by is the hyperbolic cosine, or the cosh, of 0.05 plus sinh, or the hyperbolic sine function, of 0.05 times j, which is approximately equal to 1.00125 plus 0.05j. And you can see on the coordinate grid, if the point 1, 0 is right there, this is just slightly to the right and just slightly above that number 1 plus 0j. So what that means is that multiplication by this point, since it has magnitude 1, it's going to keep all of those dots on the same hyperbola. And since it's close to doing almost nothing, since 1 plus 0j did almost nothing, it's going to exert just a little bit of motion. Let's now have a look. So here I have, as I had before, a bunch of split complex numbers, each one represented by a dot. And now I'm going to multiply by the number b that I just told you about. So this would be ab. This would be ab squared, just multiplying by b again. This would be ab cubed. And finally, ab to the 4th power. And hopefully what you're seeing here are these hyperbolic trajectories. And you can also notice that there's a very specific direction to each one of the trajectories. That is to say, all of the trajectories in this cone move in this manner. They go from bottom to top. And everything in this upper cone goes from left to right. The key property that I wanted to really explain in this video, and if you can get anything on this video, it would be this. It would be the magnitude of AB, where A and B are two split complex numbers, and the magnitude is understood in the hyperbolic sense, then the magnitude of AB is equal to the magnitude of A times the magnitude of B. And this is what keeps AB on the same hyperbola as A when B is chosen to be of unit length. When B is chosen such that the magnitude of B is equal to 1. And as a few last minute comments, just to share some other interesting information with you about the split complex numbers. Now in the complex numbers, if you've studied complex numbers at all, if I take some number ix and I exponentiate it, that is I take e to the ix power, this is the famous Euler's formula that e to the ix is equal to cosine of x plus I times sine x. Now in the split complex numbers, if I take j times x and I take e to the jx, there's an analog to Euler's formula in the split complex numbers. And it turns out that that formula is e to the jx is equal to cosh x, where cosh is the hyperbolic cosine, plus j times sinh x. where sinh x is the hyperbolic sine function. And I'd like to quickly prove this modified Euler's formula for the split complex numbers, since it's quite interesting. Now, I think the most intuitive proof of Euler's formula uses Taylor series, and I'm going to do the same thing for the split complex numbers. And I'll remind you that e to the x is written out as a Taylor series in the following way: 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial, and so on. And now what I'm going to do is simply plug in jx into x. So I just make that substitution. It means that e to jx is equal to 1 plus jx. Just making that substitution. I have jx squared over 2 factorial. I have jx cubed over 3 factorial plus jx to the fourth over 4 factorial. And the last term I'll write is jx to the fifth over 5 factorial. Now I'm going to do some simplification. First two terms, not much I could do with that, 1 plus jx. However, in this term I have j squared times x squared. Now j squared is going to be 1, so that leaves me with x squared over 2 factorial. Next I have j cubed times x cubed. Now if j squared is equal to 1, just multiplying both sides by j, that means that j cubed is equal to j. So that means I can just write j times x cubed over 3 factorial. And now in this term, I'm going to have j to the fourth times x to the fourth. Going back over here, multiplying both sides by j once again, I get j to the fourth is equal to j squared. J squared is also equal to 1, so that means j to the fourth is equal to 1. So that means that this term can be written simply as x to the fourth over 4 factorial. And hopefully you can see this cyclic pattern where the even powers of j are going to be 1 and the odds are going to be just j. So now I have j to the fifth, which is an odd power, so it's going to be j, just j, times x to the fifth over 5 factorial, and so on. And what do we notice here? We notice that all the terms of even degree, we have the 0, the 2, the 4, and then the next one will be the 6. All the terms of even degree form their own power series without a j in them, which is going to be 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial. Next one would be x to the sixth over 6 factorial, and so on. We have that power series. And then we have the terms of odd degree, which are going to be these ones, which still have a j left in them. And those form their own power series. So if I collect all those terms of odd degree and factor out a j, I get plus j times, the first one's going to be x, the next one's going to be plus x to the third over 3 factorial, the next one's going to be plus x to the fifth over 5 factorial, then one more will be x to the seventh over 7 factorial, and so on. So you can see that if you've seen the proof of Euler's formula for the complex numbers, it's quite similar to this, but if you remember in that proof, we started to get sign flips because I squared is minus 1, whereas here we get no sign flips. So that's why we're getting a slightly different pair of power series coming out here. And now I claim that this power series here is equal to cosh x, and that this power series here is equal to sinh x. So I'm going to have j times sinh x. And that's all equal to e to the jx. And I think that'll wrap it up for this video. Thanks for watching, and I hope you've enjoyed listening to this discussion of the split complex numbers, and hope you learned something new. And if you enjoy my videos, feel free to subscribe to my channel, like and comment on the videos, and hopefully you stay tuned for more videos.